So we are Group FT12 and our title is Comparative Evaluation of Models for Facial Expression Recognition. Next. So I'll be talking about introduction and background. Facial expression recognition is a task in machine learning and computer vision that involves automatically detecting and interpreting human emotions by analyzing various facial features such as movement and position of the eyes, eyebrows, mouth, and other facial muscles. These patterns are then mapped to categories like happiness, sadness, anger, fear, surprise, or neutrality based on label image data. Next. So the applications are security, which helps to identify suspicious behaviors, healthcare, which helps to track emotions for mental health patients, robotics, recognizing emotions of humans by robots, which helps the robot to adjust its behaviors accordingly. Lie detection machines can be used by police or law enforcement officers during integrations. Next. Challenges in FPR are facial concealment. Objects such as glasses, hats, hands, nose rings covering the parts of face can hinder the system ability in detecting expressions. Data inconsistency, variations in lighting, subtle expressions. If the expression is not visible, then it poses challenges to the accuracy of the model. Low resolution images can hinder system ability to detect expressions. Next.
Jiahui, I'll be sharing about our models and the project objectives. So we'll be using three models, CNN models. It identifies spatial patterns such as edges, textures, and shapes. And the deeper layers of CNN models will capture more abstract facial features such as eyebrow and mouth. We choose CNN models because of its automatic feature extractions and its responsiveness to noise of input images. Next. The second model that we are using is the ResNet 18. It recognizes a pattern of images and is made out of 18 layers. Uh, the layers can be classified into three: early, earlier, early layers, middle layers, and high layers. We choose this model is because of its effective feature extractions, and it utilizes the residual network connection that can bypass layers, facilitating quicker convergence. Next, the third model that we are using is the efficient Net B0. So it's built with three blocks, MP convolutional block that captures subtle facial features, SQ block that highlights expressive facial regions, and the compound scaling blocks that balance the depth, width, and resolution. We choose this model is because it's efficient, it has higher accuracy with lesser parameters, and is focused on the relevant facial features. Next. So next will be our project objectives. Next. So our aim is to compare and evaluate the performance of the three models that we have chosen, and all three models will be using the same dataset, RAFDB. Next will be Qingyuan, who will be sharing about the CNN model results.
Okay, my name is Zhang Qingyuan. I will show you about our CNN model. Next. In our CNN model, we designed four conventional layer, and the main role of the four layer is to automatically learn special feature from the image. And you can see this is our four layer. Next. And also we designed two for connected layer, and we use activation function to increase the non-linear ability as well as setting dropout to prevent overfitting and improve the generalization ability. Next. Here are the result of training of the model. We set up an early stop, and you can see our the best accuracy is 81.26%. Next. This graph shows the changing in loss and accuracy during the training of the model. From the left picture, we can see both training loss and validation loss are decreasing. For the right one, we can see the training accuracy and the validation accuracy are increasing, but in the final stage, it has a little overfitting. Next. And the reason of the slight overfitting is that the dataset is unbalanced. The dataset we choose is RAFDB. You can see from label 4, it has 4,000 files, but for label 2, it only has 200 files. So our model is more likely to memorize feature of the majority class and underlearn the minority class. Next. It also can see in here, the label 4 has 1114 image correctly classified, but for label 2 it only have 228. Next. So there is show 4 image correctly and 5 correctly and 5 incorrectly classified image. Okay, we will show you about our ResNet 80.
So my name is Xinyu, and I will show our ResNet results. So we use the pre-trained ResNet 18 model from PyTorch and load all the pre-trained weights. We replace the original full connected layer with a custom one. We add the dropout to prevent overfitting and the linear layer to map the feature maps to the number of classes 7. The best accuracy on validation set is 85.37 at epoch 14. Then as a loose curve and the training and the accuracy curve during training and the validation. The training accuracy rise quickly and approach 100%, but validation accuracy stable at around 82% after 7 to 10 epochs. This means the overfitting has already happened. So the reason why overfitting occurs in ResNet 18 include the ResNet have many huge count of parameters like millions, which tend to memorize the training samples from small datasets. Another reason is the class imbalance, which makes it difficult for the model to generalize to in a few classes. The dataset itself being small, which makes the model tend to overfitting the noise in the training set. So this is a classification report and confusion metrics. We can see the class 4 achieves the highest performance, but class 2 and class 2-3 perform relatively worse, and their F1 score are lower than all the others. This indicates the impact of the class imbalance. So this is a sample output from the ResNet 18. So next is efficient net.
Next. So we use a pre-trained efficient model from PyTorch and load all the pre-trained weights and replace the originally fully connected layer and reach the highest accuracy at around 83%. Next. So the training loss decreased continuously until 0, where the training accuracy achieved 100%. This shows that the model has almost memorized the training data. The validation loss reached the minimum value very early at around epoch 3 to 5, then it increased steadily while the validation accuracy remained constant at around 83%. So it means overfitting occurred. Next. So here are some reasons that cause overfitting. The first is insufficient training data, class imbalance, and deeper network model. Next. So here are the pictures showing the classification report and confusion matrix. We can see class 2 and class 3 have poor result on recall and F1 score. This is consistent with earlier observation and highlight the negative effect on class imbalance. Although the model is a powerful architecture, its complexity makes the model more prone to overfitting, especially in imbalanced dataset. Next. And here are the sample output that show the correct and incorrect prediction from the model. And next, we continue to our conclusion.
Hi, I'm Wei Yao, and I'm going to talk about conclusion. Next page. So in this project, the three models that we use are custom CNN, ResNet 18, and EfficientNet V0 to perform facial expression classification. All of these models were evaluated with the same training setup and data augmentation pipeline to ensure a fair comparison. Next, I'll talk about the challenges that we faced. The common challenges that we face across all of our models are class imbalance, in particular class 2 and class 3, as these two classes have fewer training sample and lower F1 score. This limited the model's ability to generalize minority classes, as there's not enough training sample and the total size is small, which contributed to overfitting for the deeper architectures such as ResNet and EfficientNet. I will now talk about the factors that contribute to the performance for the different models. So the first factor is the quality and size of dataset. Low resolution images and limited data can make it difficult for models to learn features, especially the deeper models. The second factor is class imbalance. So class imbalance can lead to biased predictions where the model performs well on majority classes but poorly on minority ones. The last factor is the model structure. So in our custom CNN model, we added 2 fully connected layers to help the model capture more complex patterns and improve accuracy. This shows us that designing model complexity in proportion to the dataset is crucial for reliable generalization. For future improvements that we can focus on, so we can try and balance the dataset by collecting more samples for underrepresented classes or applying over techniques such as synthetic oversampling. For deep network models, we can use a bigger dataset, especially for transform learning backbone models, so as to leverage their many parameters without overfitting. We can also freeze part of the model structure for trading, especially for models which have a huge number of parameters, so that only the higher level representations adapt to the dataset and minimize the loss. So that's it for our presentation. Thank you.